All right, welcome back. This time, we're going to go into a little more detail on Objective-Vec, which we mentioned a little earlier. Before we get started, hit the like button, subscribe, and share this with anyone you know taking the AWS Machine Learning Associate exam. So, Objective-Vec, learning relationships beyond words. So, word embeddings revolutionize natural language processing by representing words as dense vectors where semantic similarity manifests as geometric proximity. Real-world machine learning problems often involve relationships between entities far more complex than individual words. Users and products they might enjoy, genres in the content they describe, customers and the items they purchase, or documents and queries they should match, right? Objective-Vec extends the embedding beyond individual words to arbitrary paired objects. So learning representations that capture semantic relationships between heterogeneous entity types. This generalization enables applications that Word2Vec's word-focused architecture cannot address, from recommendation systems to similarity search across disparate object types. Okay, so what's the architecture of this? All right. Objective-Vec's innovation lies in its dual encoder architecture, designed specifically for learning from object pairs rather than individual items. Unlike Word2Vec, which processes single words in context, Objective-Vec accepts two distinct inputs simultaneously, learning representations that capture their relationship. Each input follows its own encoding pathway, enabling the algorithm to handle fundamentally different object types within the same model. A user item recommendation system might encode users through one pathway and products through another, with each encoder specialized for its input type's characteristics. The algorithm supports three encoder types for each pathway: average pool embeddings, simply average token embeddings across sequences, providing efficient encoding for simple representations. Convolutional neural networks capture local patterns and feature combinations through learned filters. This is effective for inputs with spatial or sequential structure. Bidirectional LSTMs process sequences in both forward and backward directions, capturing long-range dependencies and contexts that simpler encoders might miss. The key flexibility lies in mixing encoder types across pathways. A genre to description mapping might use average pooling for categorical genre inputs while employing BiLSTM for rich text descriptions, with each encoder optimized for its specific input characteristics. After independent encoding, a comparator layer evaluates the relationship between the two embeddings, followed by a feed-forward networks that produce final predictions. This architecture enables the model to learn both individual and object representations and the relationship function connecting them. Okay, understanding the training process. Objective-Vec works and learns through supervised training on labeled pairs, where labels indicate relationship strength or type. For recommendation systems, labels might be binary: user purchase product or continuous user rating. For similarity tasks, labels quantify how similar two items should be considered. The training process optimizes embeddings such that related object pairs produce similar combined representations, while unrelated pairs yield dissimilar outputs. This optimization creates an embedding space where geometric relationships reflect semantic connections. Users cluster near items they'd enjoy, similar documents grouped together, and related genres map close to appropriate content. The learned embeddings serve dual purposes. During inference, the model can predict relationships for new objects pairs using trained comparator. Alternatively, the embeddings themselves become valuable features for downstream tasks, enabling similarity search, clustering, and enhanced representations for other models. Okay, data preparation, excuse me. Objective-Vec requires careful data prep, transforming arbitrary objects into integer sequence representations suitable for neural network processing. This tokenization process varies by object type, but follows consistent principles. For categorical objects like user IDs or product identifiers, tokenization assigns unique integer indices to each entity. A user catalog might map user 1 to token 15, user 2 to token 42, creating a vocabulary of user tokens. For text objects like descriptions or queries, standard NLP tokenization converts words to integer indices in a vocabulary. Common preprocessing includes lowercasing, handling punctuation, and managing out-of-vocabulary terms. The critical requirement is consistency. The same object must always map to the same token sequence across training and inference. Maintaining vocabulary files and tokenization logic ensures reproducible transformations. When you format training data pairs, as data, when you format training data as pairs with associated labels, each example contains two tokenized object sequences and a label indicating their relationship. When you do this, you save the format in a JSON or a record.io.protobuf format and upload it to S3 for training access. Okay, so let's go and get a little bit of hands-on learning. All right, SageMaker AI. We'll go over here to training jobs, create a training job. We'll say Object2Vec dash text dash test. All right, the IAM role, configure that. SageMaker built in, scroll down here. Object2Vec, tabular. There we go. All right, so first things you're going to do, you're going to have this uploaded to S3, right? In your bucket, naming it something like training job.json, right? That for your training data, and then something like validation.json for your validation sets. Once you're there, you configure your IAM role here, like we just done. You choose your built-in algorithm. Then your next basic step would be your input. So select that S3 that you just dropped your JSON document into. Make sure you have it set for application JSON lines, all right? And then you could also do, well, you could do, what is it? X record IO slash buff. Oh, yeah, X record IO protobuf for record IO format, right? And then from there, you can do your hyperparameters, right? Like we normally talked about. But there's similar things throughout all of this. Learning rate, right? From here, this is for the gradient descent step size. Moderate value would be 0.001, 0.001. Oops, excuse me. And adjust it based off the loss curve. Then you do the mini batch size, which would be here. Okay. And it goes between 32 to 256, depending on the sequence length. And then let's see. Which one looks good? Why am I not seeing it? Wow, they took that out, didn't they? Ah, encoder dim. There you go. Okay, so this is where you define the embedding dimensionality. The values are between 128 and 512. I don't know why it's up this high. Oh, no, it's because we should be on this one. Okay, so okay, so you can set this between here and here as well. Sorry. All right, encoder network. So you can choose, oops. What's this? Oh, there we go. Encoder network. All right, so you can choose BiLSTM to do bidirectionally, HCNN, or the different pooling embedding, right? To process this based on your input characteristics. Then, let's see. Weight. All right, so you want to choose your weight decay to prevent overfitting. So you can start with a smaller one, 001. Yeah, and then dropout. And so dropout would also do overfitting. So you'd want that around 0.1. All right. And you can adjust this based on your validation performance. Also, instance, I forgot to talk to you about that one. Okay, so MLM4 is a solid one. You can go even smaller, MLM5, but I'd say somewhere around here. and a little bit larger between these two that you just saw, right? For larger data sets, when training is time is prohibitive, you can go for the GPUs, and that'll be the P series. So P2, P1. Okay, here are the P series, right? For accelerated compute, an ObjectiveVec will support single machine training only, but can use multiple GPUs on a single instance for improved performance, right? And then you configure your volume, storage. There we go. Storage per gigabyte starts at 50. All right, for a moderate scale operation. All right. Once you're here, you can launch a training job after, after you set your output path and your checkpoint path and operational tags, create the training job. And then the training duration basically varies based on the data set size, encoder complexity, instance type, right? Small data sets might be done in minutes. Larger ones could take hours. You should monitor it in the SageMaker dashboard, or you can use CloudWatch logs. All right. And when you're done, the tokenized objects and will return embeddings for the inputs and combine relationship scores, right? And so this can enable similarity calculations, clustering, and enhance feature representations for future models. But we're not going to create that. We're going to hit cancel. Okay. All right. We just went through some of that. All right. So what are some strategic applications, right? ObjectiveVec's flexibility enables diverse applications beyond traditional recommendation systems. So an e-commerce platform could use a user item embedding for personalized product suggestions, with embeddings capturing both user preferences and product characteristics that align. Content platforms can employ ObjectiveVec for genre to content mapping and learn which descriptions, tags, or metadata align with specific genres. So these embeddings would improve content categorization and recommendation quality. And a search application could use query document embeddings to improve relevance ranking, learning which document characteristics satisfy specific query intents. So this semantic matching extends beyond keyword overlap to true relevance understanding. And so the clustering applications leverage embeddings for grouping similar objects, whether users with comparable preferences, products with related characteristics, or documents covering similar topics, right? So the learned embedding space supports these clustering tasks. All right, and then cost. Let's go over here. That's embeddings. So that would be more specific. How do you get this to operate the hyperparameters that we were going over when we were in the actual training over here. All right. Okay. Okay. So pricing. So similar to others, right? ObjectiveVec's machine training constraints basically limits the horizontal scaling, but it simplifies resource planning. So you have to choose the instance type that balances training time and requirements with hourly costs, right? The GPU instances can accelerate training, but cost more per hour. So you need to evaluate whether reduced training time justifies the higher costs for your specific workload. For inference, GPU instances provide better throughput for embedding generation than the CPU alternatives, despite the higher costs. The performance advantage often justifies the expense for production applications with those real-time requirements. So consider batch transformations for offline embedding rather than persistent endpoints when real-time inference isn't required. So this will basically be more efficient without ongoing hosting costs. This is basically SageMaker's generalization of word embedding concepts to arbitrary object relationships. If you support this, it can help enable applications requiring semantic understanding across multiple entity types. We talked about the recommendation systems, similarity search, document query, and it can maintain like an intuitive appeal of embedding-based representations that made something like Word2Vec a successful endeavor. Okay, we are done. Thank you for joining. Before you go, hit the like button, subscribe, and share this with anyone you know taking the AWS Machine Learning Associate exam. Thank you. Have a good day.